Hello to everybody. Welcome to my talk. Today we will talk about so-called the constructability problem. This is the third talk in the series of philosophy of computer science. The presentations and the problems I present in this series are actually quite novel. Of course, I'm not the only person who is talking about the philosophy of computer science. Nevertheless, the topics that I handle in these talks, I think, are quite novel and new. Okay, here and there I presented some of them, of course. First, the table of contents. First, I will briefly introduce the philosophy of computer science series, which I have started some months ago. Then I will talk over symbolic world and physical world. And then I will talk about the constructability problem. Then I will give some examples of our research and development work. In particularly, I will refer to our work. And I will give conclusions. Well, philosophy of computer science series. In these series of talks, we discuss a number of inherent problems. So what are inherent problems? There are no easy solutions can be found for these problems. And I don't really expect a direct usage of this knowledge, but of course you may profit from this information in some way. But nevertheless, our intention is to widen our views and understanding the fundamentals of science and engineering. So my intention is, as planned now, I will have the following talks. So I have already talked about imperfect information, and then I have talked about early decomposition and ambiguity resolution in my other presentations. Actually, these two represent three different inherent problems. Today, I will talk about constructability, and then in order, I will talk about in the future other topics like hermeneutics and measurement problem and so forth. And these are the inherent problems which I have discovered and experienced myself, and I try to give explanation to these problems. Well, what are inherent problems? Inherent problems are the problems that cannot be solved perfectly. Nevertheless, of course, you can have acceptable solutions in practice. And very interesting feature of these problems are in the problem space. So they are inherent problems and also inherent in the problem domain. That means they are not really necessarily related to solution technologies. In other words, no matter technology what you have, no matter how much you advance in science, you may never solve these problems. But of course, acceptable solutions can be found, possibly. Competences for solving inherent problems perfectly cannot exist in our physical world. The problems, of course, what addressed in this talk are general in nature. So it means they are not really specific to the computer science, but because of my background, I present them within the context of computer science. Well, what is the philosophy of science, philosophy of computer science? I think you can find this information in my other presentations. I didn't want to repeat these definitions again and again in my every talk. So what is then the objectives? So my claim is knowing what we cannot be knowing. That is a very important thing to know. So in other words, I consider it personally my personal revelation. So what is that? So there is an imaginary boundary which we can never reach in practice. And beyond this boundary, there is an imaginary universe of non-physical competences. And we are living in this part of the universe, and the progress in science will brings us closer to this wall, to this border. Well, you may say, okay, if these problems are not solvable, so why bother us? Well, we also know that medical science tries to prolong, improve our lives, despite we all know that we all die in the future. But still, we do research in medicine. So you can consider it like that. So let's talk about symbolic world and physical world. Well, here is a text, balloons in Cappadocia, okay? So bicycle in Amsterdam, 4 slices of pizza. So when we read this text, then we can imagine something. We consider this way of representing the reality is a symbolic way of representing reality. And assume that these are, of course, real pictures, but assume that the nature is there, where balloons in Cappadocia are there. So this is called physical world, and the other descriptions are called, the first descriptions I presented are called in the symbolic world. And this is a bicycle in Amsterdam, and here are 4 slices of pizza, 1 big slice, 3 little slices. So when we look at an example of electric circuitry, for example, we see that there is a picture there where there are light bulbs and ampere meter is measuring. And on the left-hand side, there is a lady presenting the formula of what is called Ohm's law, sometimes Kirchhoff law, because of the current going through the circuit. And it actually refers to the concepts of current, voltage, and resistance. So the left-hand side, we see the symbolic world, and right-hand side, we see the real world or physical world. So most of the time we go from physical world to the symbolic world, for example, for modeling and analysis, and from symbolic world to physical world for design or realization. So when we try to analyze these within the context of engineering, we can say every engineering discipline is in fact a problem-solving discipline. When we look at this picture, then we see that we have requirements. Because of requirements, we have problems. We may divide problems into multiple pieces. And then we have solution domains. Only 2 of them are shown. And then from solution domain, we select solutions and we compose them. So this is what we call problem analysis. And this is what we call solution domain analysis. And this is called synthesis. Basically, synthesis means composition. Many times it refers to design or realization. And this is what we call verification, to see if our solutions solve the problems or fulfill the requirements. Well, let's give an example, a very trivial example. For example, this guy wants to buy a carpet for his room. And the question is how many square meters or which carpet, right? You have to select the carpet. Let's assume that cheapest available carpet will be bought. And the area can be computed from his room, dimensions of the room. So which is A times B. and then you have the carpet, and of course you would like to know if the carpet satisfies the requirements. Many times this is called verification. So this is an example of a very simple case of a problem-solving process. Now, what we realize in the traditional engineering disciplines, analysis is in the symbolic domain by using most of the time mathematics and sometimes logic combined with mathematics, but synthesis is in a physical domain. This is an interesting observation, which I will also refer to computer science, because many times I receive questions like, what is the difference between software engineering, computer science, and other engineering disciplines? I think this is a very good explanation to understand the differences. So in software or computer engineering, both analysis and synthesis are in the symbolic domain. So this is actually a remarkable difference. So when we look at all these computers, so we have on the left my laptop. This is a data center, and this is a supercomputer, K computer from Kobe, Japan. By the way, they replaced this computer with the new one. And the director of this is a good friend of mine in the past. Here we see mobile phones. These are also, of course, computers, and TV is a computer. And this shows that we like to jump from one technology to another. We have to continue to renew ourselves and technology. So for all these computers in general, synthesis is realized in the symbolic domain. But remarkably, also for mechanical automata, or you can call them maybe also mechanical computers, for just relaxation, I will show you a film, which I took some years ago, I think 20, 30 years ago. This is an automata from Switzerland, from a museum there. And this automata can be programmed in some way. And it really writes meaningful text. And it's several hundred years old. And actually, you don't see it really, but it gets ink from the pot. And when the light is off, you may call it, if you want, a robot, robots sleeps. And when the light is on, wakes up and starts writing again. And even this automata or computer is symbolically programmed. But of course, symbolically written programs are not electronic or electrical signals, but they are mechanical elements like gears. And the modern ones are, for example, punch on a card or a tape. So here, even here is synthesis. Of course, I'm referring to its automata part, is realized in the symbolic domain. So let's now look at the constructability problem. So when we have a symbolic the domain, let's say a simple program, and we have processors, for example, to convert the symbolic synthesis to some physical activities or events. Of course, this can be a processor, it can be digital analog converter, it can be a stepper motor, for example, electrical motor, which can be controlled digitally and so forth. So you need to bridge symbolic world with the physical world. And this bridge represented also symbolically, by the way. And then but in practice, we may use multiple bridges because of the difficulty of building a one bridge only. So for example, you may express your solution in a domain-specific language, which can be transformed into language like most of the time C, C++ maybe, but many times C. And then you may transfer it to machine language, which can run on real machines. And of course, as I said, there may be other devices here, like stepper motors or digital analog converters. So what is then the constructability problem? Constructability problem is an inherent problem. It is the challenge of finding the optimal way of constructing the bridge between the symbolic world and the physical world, which means that in principle, there is no optimal solution, but we can talk about an acceptable or suboptimal solution given certain constraints, of course. So what does it mean? Basically, this problem is defined by or constrained by two constraints. One is called abstractness constraint. So what is called an abstractive constraint? So here, what I show here is that you have a model, computation model. This could be a program, but I have here a high-level representation. This is an UML model. This is some sort of an architectural description language, or also called ADL. And we have a processor here. So we want to go from symbolic world, we want to build a bridge to a physical world. So what is abstractness constraint? Well, the computation elements, like you see here, must be abstract enough to match the elements of solution domain concerns. So in other words, what we want to do is actually, we have an abstract solution and we want to match actually exactly as they are. So we want to execute actually the solution domain concepts as they are, or we want to be as close as to the solution domain concerns. But at the same time, we must be concrete enough to match the processor elements or the abstractions of processor or lower level computation elements. So we cannot be too abstract or too close, because then the gap to realization, the gap to physical reality is too high. Of course, in traditional way of dealing with this is to code what you see here, a solution in some programming language. But then you again compromise the level of abstraction to the abstractions of the programming language. You may use domain-specific languages, as actually you may have also higher level of course, abstractions, like you can actually maybe express the solution in mathematical way, but then your gap to realization becomes more and more, and then it's difficult to bridge the gap between solution domain to the realization domain. Another constraint is a standardization constraint. You may address this problem by building dedicated machines that can represent your solution in a very direct way. In other words, for each problem you solve, you make a dedicated processor. So standardization constraints say that elements of computation processors, so in other words, processors, so the realization of physical domain or the final edge to the physical domain must be standardized to ease sharing among multiple solution domain concerns. So in other words, you would like to standardize the processors or the underlying platforms for economical reasons. Because developing processors are expensive, you cannot develop processor for each application or each solution. But on the other hand, for getting closer to the models that you have, you must be different enough to match the needs of multiple solution domain concerns. So the problem here is that On one hand, for economical reasons, you want to use the same processor for every application. On the other hand, you want to get close to the application to minimize the gap between the abstract model solutions to concrete physical implementations. So in other words, we have such a two-dimensional constraint space. Here, when you go, you become more and more abstract. When you go abstract, then of course you are getting to the closer to the solution domain. That's what you want, because you want to execute actually your knowledge of solution. On the other hand, the gap to reality increases and it becomes more and more difficult, sometimes even impossible, to efficiently obtain a realization. So many times what happens is that if you have an abstract model, even a model like, let's say, state machine, and if you want to compile it to real machines, then many times you have to annotate with very low level details, which actually, of course, remove the beauty of your solution, because many realization details are actually embedded because of the reasons of efficiency and so forth. On the other hand, here we have a processor. We would like to build general purpose. We want to adopt general purpose. On the other hand, when we have general purpose, the gap to bridge is, let's say, higher and therefore more difficult. If you want to build dedicated ones close to the abstractness, then of course it is easier to bridge the abstraction level. On the other hand, then it's not economical, because then you need many dedicated solutions, processors. So you may think of it as a space where feasibility space. Ideally, you want to use a very general processors for very abstract solutions, which is difficult to realize because of the gap. So you may use very general or very dedicated ones, and then you have to bridge the gap. So the question is how to come to a higher level of abstractions. So in the past, of course, in the last, let's say, 3 to 4, 5 decades, people tried to invent higher level programming languages without, of course, compromising too much over the efficiency of computation. And with the advancement of technology, of course, then we can build faster processors. On the other hand, still, there are many problems where the gap is too high. That means we cannot be too abstract because when we have to build dedicated processors, but then it's not very economical. So we can do it in only for very few cases. Actually, what we see is graphical processors or the I/O processors and so forth are some examples, but then we see them in a very restricted areas. So general purpose is most of the time used, but then the compilation or the building the bridge is more not very trivial. In fact, if we really draw a more realistic space, probably it should be such a curved space. Of course, this is just an estimation that here the gap is less, but then here the gap is higher, but the distance, the gap is higher, but then we are getting to more general purpose computers. So probably we will, in a more realistic drawing, we have to draw such a curved space. So how to deal with this problem? Of course, I will talk about research activities in the last, let's say, 50 years related to that. But in principle, if you really want to solve this problem perfectly, then you need to have these, I think, properties. Well, all symbolic means that we are living in a symbolic world. So in other words, we don't have a physical world or symbolic world. Imagine there is a world which is symbolic in nature. So don't ask me what kind of world is that, but it's the world as we program or we express models in mathematics, as we express in computer programming or computer models. Assume that the physical world is the same as our computer models, but we don't have this world and we don't know what it means and how we can create that. Okay, we create them partially in our computer, but then we have to build these bridges to go to physical reality because our syntheses in computers, as I said, are in the symbolic domain. So all symbolic is an imaginary world and imaginary competence, which we don't have. The second one is all transforming. That means we have the capability. There is a transformer which is capable of transforming any symbolic notation to a physical reality with no extra cost or with no trouble. So just like that. Okay, so we don't have, unfortunately, such transformers, and we can also discuss that such transformers are not possible to build. The third is that all infinite means that we have infinite resources, which means that we can build for all solution domain a processor, dedicated processor. So all the required resources are infinitely available for mapping any symbolic model to a physical processor or physical reality. Well, the problem is even if you make a dedicated processor for a solution domain, most of the time you have to synthesize multiple solution domains. So that means that even if you build for every solution domain a dedicated processor or dedicated bridge to reality, then you still have to deal with multiple compositions of different solution domains, which may create a new solution domain, which is an emerging property, and that is by itself, again, a problem. So all these competences, which I was thinking what kind of competences we need, you may come up with your own competences, but these are, of course, non-physical competences. So when we draw the famous wall, these are on the other side, and this is the world of the constructability problem, and this is an imaginary world. And of course, by introducing new languages and technology, we want to get closer to this wall. So when we look at the research and development work, and actually, as you know, my intention here is to let you think and try to understand the fundamental concepts of science, living, if you want to call it, engineering, and computer science. So that's my first objective. But of course, there have been a number of research work, actually a lot of work, in building more abstract machines and to increase the level of computation. So basically, what we see here is that many people try to work on increasing the abstraction level of computation. Historically, people define this as first, second, third generation programming languages. Well, you can discuss, of course, if Java is third or C++ third generation, but in principle, these are considered third generation. You know, this is an old classification. Let's say in the year 1990, 80 people were using this classification. I think to some degree it's still valid. Fourth generation, people refer to application generators. And fifth generation terminology came from a big project from Japan, where they had these fifth generation computers. Basically, these are logical programming systems, what they call knowledge systems. So here you build inference mechanisms using logic. This is again a historical term coined by a Japanese project, which I was at the closing ceremony of this project, by the way. And then, of course, there will be many programming paradigms: reflective programming, aspect-oriented programming, future-oriented programming, and programming emergent behavior, etc. And we see also in the year 1990s emergence of model-driven engineering, where you try to define models, and these models are computable, which means that you can run these machines, models as they are, or transformational system design. You can transform models to executable code, or from one model to another. And there also work on special language constructs like user-defined events and abstraction mechanisms, and user-defined composition operators and abstraction mechanisms, and so forth. Of course, there's a lot of work on compilation and runtime optimization of programs and software systems. Well, when we look at it, of course, when we look at these, especially now I'm referring to our research work because it's too much to name all these, but I can say that we were one of the pioneers in many of these technologies in the past. So actually I published this constructability problem, I think 2004, yes, 2004. And I call them abstractness constraint and standardization constraint at that time, and was not maybe that much understood, but nevertheless, I think the idea is, I believe, not too difficult to understand. But okay, so this was published at that time. And then, of course, we introduced many language extensions to increase the language expression power. For example, Uppsala 88, we have the Sine language, where you could actually inject so-called cross-cutting behavior. I think this was one of the first, if not the first, aspect-oriented language. And then we had many papers, what we refer to as composition filters. I believe still that very powerful language mechanisms, especially we were focusing on domain-specific solution models, so similar to domain-specific processors, but our focus is to compose these multiple domains together, because that's actually the main problem. You may make very specific language models for certain domains. For example, here, synchronization and real-time domain in this paper, but how do you compose them together is a serious problem, and we focus on that. There is here communication of the ACM publication, for example, and then this later became this terminology, composition became aspect-oriented programming, and adopted by a larger community. Here, for example, we show some of the papers, actually as early as 1988, where we express user-defined composition operators. And then here we have also user-defined composition operators, which actually a way of expressing the abstractness level, but also by defining user-defined composition operators, you can also ease actually the compilation process. So the software engineer defined execution composition operators, and by using very primitive event-based mechanisms, you can do that. And this is actually, these are publications which you, one step further, where you define emergent behavior, which means that when objects come together, a new behavior appears, and these are very difficult to handle because they appear at runtime and not always necessarily known ways. So we had here interesting work, I think, to express these mechanisms. You see all the language, model-driven engineering, compilation, runtime optimization, they all refer to actually, to some degree, constructability problem. But the problem by itself is an inherent problem that cannot be solved easily. Okay, here is a list. If you are interested, I will put it, some selected list of our publications, just to know. So what are my conclusions? Actually quite straightforward. We have, I think, a novel explanation of differences between engineering and software engineering or computer engineering. I pointed here difference between symbolic synthesis and physical synthesis. And then I have explained the constructability problem, that it actually, we cannot have one single point. It's about a region and it's about a compromise. The more, for example, you make dedicated processors, the gap to solution domain decreases, but it is not economical if you continue further on that line. If you make computation too general purpose, however, then the gap gets higher. So that means that efficient transformation to higher level concepts to lower level will be difficult. Therefore, that you have to actually add, most of the time, what I would call dirty low detail programs. So you have to make your own compromise, and this is also what we observe today. And I presented our research work and related work to some degree.